So we'll begin again. So I look up, I Google it. I can't find it in the book. I don't know if it's there, if it was in a previous edition. I'm not sure. I know it from somewhere. I can't find it anywhere. But if you look at the Wikipedia page, it did the same thing I did, except it was doing it for a non-homogeneous problem. So I had like an RFT here divided by y1 where I had 0. But it got to this. This is exactly what we got to. And it just kind of says, well, then integrate. Well, great, that's kind of useless. I wanted a formula. But then a little bit more Googling revealed this other page here. I'll put links to these on the website and Blackboard here in a bit. But so this gentleman here, some professor at Oregon State. I don't know if you see his name there or not. I don't know. Anyway, so he's actually dealing with the homogeneous problem, which is what I want. And he also gets to the same differential equation, but this is the simplification I was talking about. If you fiddle around with the exponent, you can rewrite it as you can write it as it's the integral of e to the minus integral of p dt from the differential equation, and then divided by the given solution squared, and f of t. So like an application of this equation, since I've wasted this much of our time already, let me just complete the madness. Let's see here. So the formula is, in our notation, y2 is equal to y1, the integral of the exponential. This u is e to the minus integral of p. We're using x as dx divided by y1 squared. That's an improvement over the formula I had. And so let me show you how this works out. So if y1 equals x to the power r, right? And so suppose we're looking at y prime prime plus what is it? So I'm forgetting what the p was. We started with ax squared y prime prime plus bx y prime plus c y equal to 0, right? And that gives us, I think I can put a equal to 1 without loss of generality here. And so that gives me y prime prime plus b over x y prime plus c over x squared y equal to 0. So this is my p. So I get y2 is x to the r, the integral of the exponential of minus the integral of b over x dx over y1 squared, which would be x to the 2r, right? And let's see here what happens. This integrates to what? I really should put b to be what we had in the example I was doing rather than trying to do it in general. What was my b here? B was 1. B was 1 in our example. So let me just put that there. So what's the integral of 1 over x? That's minus the natural log of x. This exponential integral just becomes exponential of the natural log of x to the minus 1. In other words, this whole exponential just becomes the integral of, we've got x to the minus 1 over x to the 2r dx, which is what? Oh, I'm sorry, what was r equal to? I should, I'm using that example, right? So what was r? 0, right? So this is really just the integral of dx over x, which of course is, there you go. And if you paid your dues and started with like the general repeated root case, you could derive the thing I claim over there using this formula. Okay, enough about that. So sorry I spent so much of our time on it. It's just, once I start something, I want to finish it. All right, so let's get back to the discussion I raised at the start, which was there are singular points. Some of them are irregular, some of them are regular. What's a regular singular point then? I'll put this away for just a bit. We'll get back to it, but so here's a definition. If we have y prime prime plus p plus py prime plus qy equals to 0, and x naught is singular point, such that how's it go? Trying not to get my notes out just yet, but I need to make sure I got the notation right here. Come on. Yeah, okay, I use a big, in my notes I'm using big P and big Q here. I'm going to start doing that now, just so it looks just like my notes, okay? So anyway, if that's a singular point such that x minus x naught times p and x minus x naught squared times q are analytic, then x naught is a regular singular point. So what that means is that P and Q are not analytic, but they're kind of not far from it, right? So what would that mean? Let's see here. Let me just kind of expand on that for a second. That means that x minus x naught times p is something like, c naught plus c1 times x minus x naught plus c2 times x minus x naught squared, right? And x minus x naught squared times q is something like b naught plus b1 x minus x naught plus b2 x minus x naught squared plus b3 x minus x naught cubed. So what does that say about p and q? There's some kind of formula for them. It looks like what? So p is something like c naught over x minus x naught plus c1, plus c1 plus c2 x minus x naught, and q is looking something like b naught over x minus x naught squared plus b1 over x minus x naught plus b2 plus b3 x minus x naught. So if it's a regular singular point, that means that P and Q don't have power series expansions, but they do have some kind of expansion like I just wrote. Do you guys know what these are? Have you ever seen such an expression before? It's kind of like a power series that goes the other direction, right? Like power series, we do positive powers of x minus whatever to a power, right? Here, I'm just throwing in a few negative powers. So a question I always ask students when I have a chance is, what do you think the meaning of the coefficients like b1, b naught, c naught would mean? What would these tell you about for the functions p and q? What does your intuition tell you that those coefficients should have to do with? Let me ask a somewhat leading question. What does C2 tell you about P at x naught? What's the meaning of this? What's that tell you about P at x naught? Well, you're like, it's not defined at x naught, so your question doesn't make sense. Fine, you got me. Curses. But if it was defined at x naught, it'd be a derivative, right? So what do you think these things?
Initial conditions?
No. Sometimes people guess. So one of the things we learn in complex analysis is that these coefficients actually tell us what the integrals are of such functions around loops that contain the singularity. This is what's known as the residue calculus. More to a point, here's some formal language for you, but these are both examples of what are called Laurent series. So a Laurent series is an extension of power series where you have just a couple of terms. You have finitely many reciprocal terms in your expansion. And it turns out that those are relatively tame. The analysis of them we can handle. Anyway, so, all right, that's just language. Really don't do much more with that. But if you look at example 4, I suppose, is if we have ax squared y prime prime plus, let me get rid of the a. Let's say x squared y prime prime plus bx y prime plus cy equals to 0. That gives me what? Y prime prime plus b over x y prime plus c over x squared y equals to 0. So p is b over x, right? And q is c over x squared. So what happens when we look at x times p? What do we get? I mean, x times p is just b, right? X squared times q is just c. Those are constants, right? So in particular, those are analytic, which goes to show you that x equals to 0 is a regular singular point for the Cauchy-Euler problem. All right? Okay. So what I'm about to show you is that the Frobenius method gives us a way to solve any problem with a regular singular point using a systematic method, much like the one we've already seen for ordinary points with power series. The starting point for the calculation is going to be to suppose that we can write P and Q in such a fashion. Right? Because we can write P and Q in such a fashion, we're going to be able to use that to simplify the differential equation order by order, just like we did for power series. So let me show you how it goes. Let me get my laser. All right. So we're going to study y prime prime plus py prime plus qy equal to 0 with a regular singular point x dot. We're going to put x not equal to 0 because there's no loss of generality in doing that. See, if I put x equals to t minus a, that moves x, that makes, t equals to a correspond to x equal to 0. And this differential equation under that substitution becomes that one. So there's really no loss of generality in just studying the 0 case, because we can always make this substitution to go back to if it was something that was non-zero. We can transfer the math over to that. All right. So this is the problem we're solving. Y prime prime plus py prime plus qy equal to 0 with a regular singularity at 0. That means that x p of x and x squared q of x are analytic at x equal to 0. So by the thing I just worked out over there for you guys, that means we can write p of x as like p naught over x plus p1 plus p2x squared. And we're assuming that q of x admits a Laurent expansion q naught over x squared plus q1 over x plus q2 plus q3x plus dot, 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 dot. All right? So, more to the point, if we multiply x times p of x, we have this. If we multiply x squared times q of x, we have that. All right? Now here's the Frobenius. The Frobenius method is just this at its start. We assume that we can find some number r. That r is basically like the big R I was using at the start of today. You can think of it as the same thing. All right? Such that, in coefficients a sub n, such that the sum n equals 0 to infinity of a sub n x to the n plus r solves this differential equation. This is the Frobenius solution. Now, before we even get any further into it, why is this different than what we've already done? I mean, isn't that just a power series? How is this different? Isn't that just a power series? I mean, well, that little r, which we called big R at the start of today, what was it? I mean, did it have to be a whole number? No. That r could be a half, it could be 2/3, it could be complex. It could be negative. So these are power functions, but they don't have to be, they don't have to be integer powers. Positive integer powers. This could be x to the 1/2 power, x to the 2/3 power. So it could be like if r equals to a half, this is something like the square root plus some number times the 3/2 power plus some number times the 5/2 power plus some number times the 7/2 power. It's like a sum of fractional power functions with appropriate weights. That is really, really different than what we've done up to this point. It just looks the same, but the content of this guess is quite different. Now, it turns out, if you do the analysis, that the term-by-term differentiation theory still works out. In other words, the derivative of such a series is the term-by-term derivative. So I can just differentiate term by term. Differentiate this, you'd have, a sub n times n plus r times x to the n plus r minus 1, right? Take two derivatives, you'd have this. Now, to actually prove that would probably take me like an hour or two, right? But you guys are kind and you don't make me prove it. You'll just be like, we'll accept it. It's cool, right? All right, well, I'll put some more words in your mouth. Let's hear. So what do? This should be totally unsurprising. I take these formulas for the derivative and the second derivative and the solution, and I plug them in to the differential equation, just like that. And I actually, not this differential equation though, I chose to multiply it by x squared to make things prettier. It's nicer to work with this one, I think. Potato, potato, whatever you want to say. But So there's my Frobenius solution. This is that expansion that we're given for P, the expansion for Q, and then here's the derivative, and here's the thing. You notice we've got an extra x, we've got an extra x squared, so those are going to conspire to make all of the power functions x to the n plus r, x to the n plus r, x to the n plus r, right? After you multiply the x squared and the x through, all of these summations match up. Does that make sense? And then what? Well, so we can combine them into one big foul, glorious sum. What do I got here? Sum n equals 0 to, I got this term, then I got that term. You see, I could have just made like really big parentheses and factored this out, you know. I'm not sure why I know why I didn't do that, because you got to think about multiplying this times that, right? You got to think about multiplying this times that. Okay, so then what we got to do is just look at this and go order by order, looking for equations, starting at the lowest order and kind of working our way from there. What's the lowest order thing in here? Is n equals to 0. I put n equals to 0 here. What does it give me? A sub 0, r minus 1, x to the power r. Right? I put n equals to 0. So to get the lowest order thing here is p naught. The lowest order thing here is a sub naught times r times x to the r. Right? The lowest order thing here, q naught, a sub naught, x to the r. So each one of these has an x to the r term. And if we collect those together, here they are down here. This gives us this equation. It gives us the a sub naught can't follow, you know, it goes out. It's everywhere, so it gives no condition on a naught. And I mean, if we shouldn't assume that a sub naught is necessarily 0. I mean, I suppose it could be 0. That would lead to a different path. But suppose it's non-zero, then that forces r times r minus 1 times p naught r plus q to be 0. This is what's known as the indicial equation. This indicial equation, the solutions of which are called indices, that's exactly what we're doing at the start of class. The characteristic equation for the Cauchy-Euler problem is its indicial equation. And that was enough for that problem. So this r in the general solution, you know, sum a sub n x to the n plus r, that r is not just an arbitrary r. It actually is forced by the indicial equation to take certain values. So at this point, you can kind of see where we're going to go with this, right? This is a quadratic equation in r, because p naught and q naught are constants. And so it's going to have three different kinds of solutions. Distinct real, right? Repeated root, and complex, right? And so those should play out a little bit different. But here's where it gets weird. That's not actually how it plays out. It turns out that if the indices differ by an integer, you have to do something different. If they're distinct but don't differ by an integer, that's a different case. So there's actually, I think, at least 4 cases here. Because the distinct root case, I'm remembering there are 5 cases. They're not all in my notes even, guys. If you look in section, so I think there's 2 sections in the text. So page 475 to 476, he has this theorem 7, which is the form of a second linearly independent solution. And he's got like, you know, he says let R1 and R2 be the roots of the associated indicial equation. And he arranges them such that the real part of the first root is larger than the real part of the second root. And then he's got like case A, R1 and R2, R1 minus R2 is not the difference between the roots is not an integer. It's more subtle than just them being integers. The difference between them, not an integer, then basically you just use the thing we already wrote twice. It'll give you 2 linearly independent solutions. On the other hand, if they are literally repeated, if R1 is equal to R2, then you get one plain old Frobenius solution like we had up there just a second ago, and then something involving natural log in a somewhat complicated way. That's part B. Part C, if R1 minus R2 is a positive integer, then there exist two linearly independent solutions of a form, which again involves a natural log in a slightly complicated fashion. It's not that complicated. I'm just saying you got to look at the book. So there are 3 cases in the real case, and then I think what he's saying applies to the complex case too. If the real part of the complex solution, he doesn't say enough for me to be sure about the generality of the method actually. So, all right, enough about that. I'm just warning you to find the second solution. It's sometimes subtle. I don't foresee me testing on that though. I don't have enough examples to really hold you accountable for it, you know? To whom much is given, much is required. I haven't given you much on expositing how Theorem 7 plays out. I just want to warn you about it. Okay, so let's get back on the straight and narrow here. So past the initial equation, if you looked at n equals to 1, you get these terms. If you look at n equals to 2, you get these terms. I don't actually use these equations. I'm just pointing out you would go that way. All right, so here's an actual problem. Let's look at an actual problem. 3x y prime prime plus y prime minus y equal to 0. X not equal to 0 is a regular singular point. This is not a Cauchy-Euler problem. This is kind of like the one I had a typo in earlier, right? Sort of like a Cauchy-Euler problem, but not quite. So here's my Frobenius solution. Differentiate. I don't know why oh, it's because I changed n equals 0 to n equals 1 for some reason. Why did I do that? Oh, it's just the quirks of this one. It seemed more natural to me to do that. Y prime is this. 3x y prime prime is that. The reason I did that, this shift of index, is because I saw that the first term and the last term, the first term and the second term would naturally have an x to the n plus r minus 1 power. So then, rather than changing both this and that to make them look like this, I just made the y change so that it looks like the first two things. The same song and dance as before. In order to add the series, we have to make the powers match up, right? Okay, so what I'm doing is I'm taking the series and I'm plugging them into this equation that gives me this monstrosity. And then I go, okay, well, this is the exceptional case, right? This has this, okay, so let's think about this. This starts at a higher order than these two, right? These two have constant terms in them, whereas this has starting at x, right? I should say starting at x to the r. It doesn't have an x to the r. This over here starts at x to the r plus, oh man, that should be a 2. This is supposed to be a 2, guys, I think. Because if that's 1, then this is x to the what? X to the r, which is this thing over here. That's a typo. That's supposed to be a 2. Sorry about that. Anyway, my point is there's a couple of exceptional cases which stem from the fact that these two don't have the x, right? So those give us this exceptional thing with the x to the r, and then I have n equals to 2 to infinity, these guys. So that has to be 0 order by order, which gives me this recursion relation between a sub n and a sub n minus 1. And here's my indicial equation over here. Well, this indicial equation we can clean up. It becomes 3r squared minus 2r, which is r times 3r minus 2. So I have r1 is 2/3, and r2 is 0. All right? So this is good. They're distinct, they're real, and they don't differ by an integer, which means I don't get into the horrible stuff in Theorem 7. All right, so then what we do is I actually, now that the point of order here, guys, I found it easier to not put the value of r into the general setup to start with. I like to find the recursion relation, then solve the indicial equation and plug it in. To do the opposite would mean that I have fractions up in here, and I'd have to find, finding the recursion relation. It's uglier if you do the indicial equation first, in my experience. So just a point. We may see me do the opposite somewhere, you know. Anyway, so if we plug in 2/3 into here, what do we get? What happens when we put 2/3? We get 2 minus 2, that's 0. This becomes 3n, right? And how about this? So I get 3n, this becomes n plus 2/3, which when we multiply the 3 through, becomes 3n plus 2. So do you guys see that? This formula specializes to this when we put r equals to 2/3. Then that's a nice formula, and I can do the usual thing. I put in 1, I put in 2, I put in 3. I keep folding the earlier ones into the later ones, looking for a pattern. After a bit, I see this is about the best I can do. A sub n is a sub naught over 5 times 8 times 11 times 14, times 3n plus 2 times n factorial? Where did that factorial come from? Oh, I see. So if you look at the pattern, we're building up, like here's a 4 factorial, and then I have 5 times 8 times 11 times 14. Here's a 2 factorial and 5 times 8. And 8 is what? 8 is 3 times 2 plus 2. 11 is 3 times 3 plus 2. So like the highest number here is always 3n plus 2 if you look at it. And there's always a factorial that you can peel off. So, yeah. Can you tell me in general how to find patterns? No, I really can't. It's not my, not one of my gifts. I know it when I see it. That's about all I can tell you. And sometimes I don't see it either, so don't feel alone. But this is the Frobenius solution with index 2/3. It's exactly this, a sub naught x to the 2/3 plus the sum n equals 1 to infinity of x to the n plus 2/3. This guy, that's my first solution. Not a power series solution, mind you, right? A Frobenius solution. And then when we take R2 equals to 0, well, actually the second solution actually is a power series solution. Because the index is 0, that means we're looking at an ordinary power series, honestly. And anyway, so putting R2 equal to 0, going back up here, put R2 equal to 0, that gives me n and 3n minus 2, as you can see, n 3n minus 2. And then I recurse, and plug that one into that one, and plug that one into that one, and plug the other 3 into this one, and then just stare at it until your eyes bleed, and you see that it's actually 4 times 7 times 10, 3n minus 2, and we can peel out an n factorial. That's a pretty, these kinds of problems, trying to see if you can find factorials to peel out. Sometimes you can see like 2 to the power n, or a 3 to the n. Sometimes you can figure out like an exponent of a specific number, which keeps repeating or something like that. These are common patterns that I've seen. But anyway, the second solution we got is y of 0 comma x, which this is just notation. This notation says Frobenius solution, index 0 at x. That's all that means. And here it is. So a sub naught, what is, that feels like a, why do I have this plus x here? Oh, again, it starts at 2. So here's n equals 0. Here's n equals 1. I guess the thing I'm worried about, guys, is why didn't this start at 2? I think this is supposed to start at 2. I'm a little worried about why is there one term here but 2 terms here in front of the sum. Granted, this one maybe this fits the pattern for n equals 1 is the idea, whereas this one doesn't fit the pattern for n equals to 1. Well, okay, this is just silly. I mean, if I put n equals to 1 here, I could pull the 1 and I could pull the x into here by putting the sum starting at 1. So it's not interesting what I'm talking about. Sorry about that. It is a little bit awkward that I've written 1 plus x here and didn't fold the x into that like I could have. I folded a x to the 5/3 appears that n equals 1 here. N equals 1, give me what? Just a 5, right? So I guess this is my question, is if we look at the n equals to 1 for the 2/3 index, is there supposed to be a 1/5? Oh yeah. See, right there. Okay. If we were spending the proper hour to slowly and methodically go through this calculation, you know, that 5th wouldn't have been troubling to me from the outset. All right, let me just pause here for a second. Do you guys understand the method? We propose the solution has the form. Woo! Oh. Oh. Home. Not. I must have hit home instead of page up. Oh. That hurt me. Fortunately. Haha. Okay. So we're solving this, and basically our proposal is that y is equal to the sum n equals 0 to infinity a sub n x to the n plus r. And we learned for that to work, we have to solve the indicial equation, which we derive shortly thereafter, right? A little bit of calculation here, and we learned that r isn't just anything. R has to solve the indicial equation. So we solve basically we plug in for our given problem, plug in the Frobenius solution, work out the indicial equation, work out the recursion for the a sub n, and then solve the indicial equation. That will find a index for us, and then plug it in the recursion, look for pattern. All right. So here was a solution. Here's another one. This one will be easier, because this we already know how to do. This is a what? This is a Cauchy-Euler problem. I have x squared with y prime prime. I've got x with y prime. I've got the y sitting on its lonesome. All right. It is a regular singular point. So when we go through, the indicial equation is the characteristic equation. We get r plus 1 squared. This gives r1 equals to rt equals to minus 1. And so if we plug in minus 1, I actually just plugged it in rather than following my usual advice to find the recursion relation before I plug it in. This is what I was talking about. So I plug it in, and it gives me this, right? And then you collect terms, and you get that. All right. So what do we get? We get n minus 1 times n minus 2 times 3 times n minus 1 plus 1. All right. So what happens with n equals 0? N equals 0 gives us 0 times a naught equal to 0. So a naught is free. A naught is not pinned down at all. But if you put n equals to 1, what happens? This is 0. This is 0. That's 1. 1 times a1 is 0. a1 is 0. All right. How about 2? 2. Oh, that's 0. This is 3. 3 plus 1 is... It's non-zero. Something non-zero times a2 is 0. And you can keep going up the chain. If you look at any n larger than or equal to 1, you get non-zero number times a sub n equal to 0, which says that a sub n is 0. So what happens when you try to do the Frobenius method to a Cauchy-Euler problem is the whole Frobenius solution just truncates into the lowest term. And that's why we just had basically x to the r. That's the first thing in this sum n equals 0 to infinity of x to the n plus r. Now, this is again the wacky case because it's a repeated root, and we learned that it's actually going to be c1 times 1 over x, that's x to the minus 1, and then c2 log x times x to the minus 1. All right. Here's an example with imaginary exponents. The Frobenius method also works for imaginary indices. So same song and dance. Here's our regular singular point at 0. I take the Frobenius solution, I plug it in. I make the summations look the same by reindexing as necessary. After a little bit of standard calculation, it gives me, this is my lowest order term, and then I've got the sum n equals 1 to infinity of these guys. So this time my initial equation, I got an r squared minus r plus 4, aka r squared plus 4 equal to 0. So the indices here, plus or minus 2i. Right? But have courage, the method still works. But it's going to give us a complex solution. So what I do is I plug the index 2i into here. That gives me this. I rationalize by multiplying by the conjugate of the denominator over the conjugate of the denominator. Doing that gives me n squared. To start with, it would give me n to the 4th plus 16n squared, but I just factored out an n squared. So I have n squared times n squared plus 16. Upstairs, I have a sub n minus 1 times n squared minus 4ni, or n squared minus 4ni. And so a1 is that. a2 is that, which I can then plug in the a1 into that. And then a little bit of complex arithmetic later, I got this guy. Yeah. These are fun. And so lots of complex arithmetic. Come on. And so what this shows me is that my complex solution is, x to the 2i. That's my, that's x to the r, x to the 2i, right? And then this is x to the 0, x to the 1, x to the 2, and so forth. And here's the, so all I'm doing is I'm just plugging back in the recursions we just found into the template solution, order by order. This is a naught, x to the r, a1, x to the r plus 1, a2, x to the r plus 2, and then I'm just collecting things. The reason I'm doing this is the real part, this is the imaginary part. I'm calling those a and b, kind of like we did before. Likewise, this is going to be cosine 2 log x plus sine 2 log x. So when you multiply this complex quantity times this complex quantity, you're going to get real minus imaginary plus I times real imaginary plus imaginary real. In other words, this. And then that would be the general solution, C1, C2 that. But the devil's in the details here. Like, I've only found the first couple terms in the power series expansions of A of x and B of x. But there it is. That's the Frobenius solution for a complex case. It's quite natural, the calculation, but it's also quite intimidating, I think. I mean, I don't know. The word beastly comes to mind. I don't think the textbook actually has an example like this, unfortunately. But, you know, I don't have everything the textbook has either, so I can't. I mean, I understand. I mean, this topic is, it wears you down. Next here, x y prime prime plus 3 plus x squared y prime plus 2xy equal to 0. Basically, this I just get straight to the point of looking at the index initial equation for a change. The exponents are 0 and minus 2. And then I plug in. Here, I don't think I follow my own good advice. I actually put in the index to start with. So, I mean, you can do that, and it looks like this if you do. I don't know. I mean, anyway, we plug in. Well, see, I plugged the, see, then I don't even know which index I'm working with. Which index did I work with? It looks like I used 0, right? I plugged in 0, the 0 index solution. And it gave me this, which gave me that. So that makes A1 equal to 0. And it makes this linear combination of A2 and A naught be 0. So in other words, like 8A2 is going to be equal to minus 2A naught. And then you got this lovely recursion thing between the other coefficients going on. So after some calculation, I get to the recursion, and I stare at it for a little bit. Eventually, I see the pattern minus 1 to the k over 2 to the k, k factorial. So here's what I was talking about. Sometimes you can see like 2's. I got 2 2's. I got 3 2's. I got 3, 4, 6 2's. Oh, 6 2's. And here I'm going to have 2k2. I've got, how many 2's do I have? I don't know. Apparently 2 to the k, 2, 2, 2, 2, 2, 2, 2, 2, 2. Huh. Oh, I got to leave some of the 2's to make up the k factorial. That's the thing I'm forgetting, aren't I? So I only pick up 1, 2 from here, 1, 2 from here, 1, 2 from here, 1, 2 from here, 1, 2 from here. What's left over is a 4, a 3, and a 2, which is what I need to make the 4 factorial. Yeah, so each one of these factors I pick up 1 copy of 2 from, which is why I got the 2 to the k. What's left over makes the k factorial. Anyway, so this is my Frobenius solution from the index 0. And this, through a quirk of fate, the other Frobenius solution, r equals minus 2, it turns out, I think, that this one actually works. So this one's kind of a very quirky. It so happens that the other one, if it ends up just being an x to the minus, x, 1 over x squared ends up being a solution for this. All of the unpleasantness I was talking about in Theorem 7 doesn't actually come to play non-trivially in this example, if I've done it right. And I think this is an odd problem from the textbook, so I think this is correct. I just think that this is not a good illustration of the trouble which is in Theorem 7 that I mentioned on page 475. All right. Let me go on here. What I'm about to tell you is probably one of the more useful things I'll share with you today. Well, I don't know. That's a wrong thing to say. The Frobenius method is really, really useful. So many, if you go on and study specific harder partial differential equations, you'll learn that the solution sets to these partial differential equations are also often given in terms of things called special functions. Special functions often arise as solution sets to differential equations which can only be solved by series techniques. A lot of times the Frobenius method is the technique which is needed to solve that differential equation. And the solution set which is created with the Frobenius solution will be given a name. The last section in your chapter is all about this. Bessel functions, Legendre polynomials, Hermite polynomials. There's a whole wide world of special functions with particular names that are born of the physical problems that they solve. And so this technique is useful, but it's hard, right? Because these kinds of complicated physical problems are difficult. And I can't take that away. I mean, it is what it is. Suppose you want to find the wave function for the hydrogen atom or something like that. You come face to face with a non-constant coefficient second-order differential equation that requires some of the techniques and generalizations of the techniques we're looking at to really solve it. And somehow you have to see past the dark magic which physicists do in these problems. But anyway, I digress. So here's two examples so far of the repeated root, right? We have, think about this. If we have a repeated root of r for the constant coefficient problem, we have said that e to the, oh man, well, come on. Golly, this is so very annoying to me. That is supposed to be a t, and that is supposed to be a t. Goodness gracious. Take a point off my notes. I'd definitely take a point off your test this semester for you doing that, right? Man. I feel like I wish I had one of those like medieval things I could hit my back with or something, I mean, I should do something. Goodness gracious. Obviously that's supposed to be right? Or you could put x's here. You could replace all the t's with x's. That would also be fine. But you see, my point here is differentiating. Hey, come back. Differentiating with respect to the characteristic value, my one solution somehow generated the second solution. And look, it happened again over here. The derivative with respect to the r of x to the r is the log of x times x to the r by the usual differentiation of an exponential function, right? We're differentiating with respect to r is the thing. The base is x, right? That is a way easier way to find it, right, than this calculation I almost completed today before the break, right? That integral solution formula I showed you for finding the second linearly independent solution. Well, this seems to me to be a much better way of thinking about it. So here's why. But the question is, well, that's great that you differentiate that and got that, and differentiate that and got that, but why is that a solution? So here's a demonstration of it. If I have, let's see here. I think I'm looking at the differential operator L being d squared minus 2 lambda 1d plus lambda 1 squared, all right? So you might notice that e to the lambda, if we take L and act on e to the lambda x, what happens? When we differentiate e to the lambda x, what happens? We get lambda squared times e lambda x. The differentiation operator gives me down a lambda. And then we multiply by lambda 1 squared, so we get that, right? So this actually gives us lambda minus lambda 1 squared. Come on, e to the lambda x. Oh, man. This thing's bugging out of me. So if we look at y1 is y1 of lambda 1, so what happens if I put lambda equals to lambda 1 here? That's 0, right? So if you look at this, when we put lambda 1, anyway, so we put lambda equal to lambda 1, we have a solution. If we consider y2 is the derivative with respect to lambda of y lambda comma x, and then after that set lambda equal to lambda 1, so what happens if we feed the differential operator partial lambda of y of this, right? Then the sneaky step is that we can reverse the order of differentiation with respect to the parameter versus the derivatives defining the differential equation. So if I flip and I differentiate the parameter second and then evaluate lambda equal to lambda 1, I will have this. But when I differentiate that with respect to lambda, that just gives me lambda minus 1 squared e to the lambda x by this calculation up here, rather. And so when I plug in, and then of course if I differentiate with respect to lambda this gives me twice lambda difference of the lambdas, and then that times x e lambda x. But then when I plug in lambda equal to lambda 1, I get 0. So this shows you that at least for this particular, so this is the argument for why it works, why this differentiating with respect to a parameter works in the constant coefficient case. This calculation can be generalized though, and you can show that differentiating with respect to a parameter will produce a second solution for a wide class of differential equations. Maybe this is the most satisfying answer as to why we have to multiply by t to get the second solution. It's because you can obtain the second solution by differentiating with respect to the parameter that defines the solution. So anyway, you can do the same thing for the Frobenius solution. In the repeated root case, if I have a Frobenius solution and I differentiate with respect to the parameter in the repeated root case, you see what I get? I get the log x to the r times this plus x to the r times that. You end up differentiating the coefficients with respect to the index in the repeated root case. This formula is not in the book. This I found in Rabenstein, which is a fantastic book, but it's a little bit too hardcore for this course. I mean, it was used for this course back in the day, but it doesn't have enough homework, and yeah, anyway, it's a wonderful book though. Anyway, so basically differentiating with respect to r shows you that, and then after that, after you're done with the differentiation, set r equal to r1, which is repeated, and that's what pops out. So that's one of the things that's in that theorem 7 I've been warning you about. All right. Again, I don't test on this, but I want you to know about it. So good news, Nathan. That was it. Yeah. Let's see here. I mean, I still have a few comments, but all right. Let us take a look at quiz 3, if I can find it. So let's just talk about these problems for a second here. Problem 1 and problem 2, these are not intended for test 2. I am going back to the thing half of you had trouble with on test 1, namely setting up the particular solution for the non-homogeneous problem using the method of annihilators. About half of the people taking this course need to think more about this before the final. So I, in my heart, believe that by really carefully doing these two problems, thinking about how you set up the YP carefully using the method of annihilators like we did, if you do that, there's a very significant chance your final exam grade will increase by about 10%. Because it's not just the setup questions that this hurts you